Welcome to ERC TipsKnowLogy. In this video, we will be learning how to create an assembly language program using 8051 microcontroller. And to do that, we will be using one application which we call as EDSIM Simulator. Now, this EDSIM Simulator is very useful in simulating some programs in assembly language that uses 8051 microcontroller. Now, as you can see, there's a part here that shows the system clock, which is a default value of 12 megahertz. And also the buffers are here, the registers, the pins, and like the R0 up to R7, the accumulator especially, program status word, and the other parts of the registers that is used by 8051. We also have here the data memory on the lower part. Now in the middle, this is where we will write our code. And for this particular simulator, the port zeros like P0.0 up to P0.7 are fixedly connected to the keypad row 0 up to keypad row 3, and then we have keypad column 0 up to keypad column 2 and the display select decoder. Now, what we will be doing is that when we want to use the LEDs, these LEDs, we should use the port 1 or P1 here, over here. P1.0 up to P1.7 is actually connected to these LEDs whose position is from position 0 up to position 7. So for this particular example, we will be trying to blink the LED here on the first LED on the right side, and from there we will be moving on with other examples later on. Now for the first example, we will be doing some program, and the basic program that we will do is to create an assembly language program that will blink the LED at P1.0. Now let us say that the LED is active low. So we will blink the LED at P1.0 or P10 with some delay. Now, unlike the previous examples that was given in this YouTube channel, we are using the C language. This time we will be using assembly language. So the LED is active low. It means that 0 will be on and 1 will be off. We can also say that high is on and low is off. That's the meaning of active low. Now to start the program, we have to declare or define where's the start of our assembly language program or assembly. So the first that you will write is org00h. Now we will just write it in capital letter, although it does not really matter, but we will write it as org00h, or you can also put 4 zeros if you want to. Some people they just put 0, org0h. Then after that, we will think of a label like main. This will be like the start of our program. You can use any word that you want as long as it is not used by assembly. So we have the main here. We can use start, okay, and you should not use reserved words or words that are really used by assembly. So you should be defining a label which is originally from you, not from the assembly. Then what we will do first is we need to move to the accumulator a certain value like hexadecimal FE H. Now, in the case of assembly, we have to put 0 when the first letter, when the first part of the hexa number is a letter. I mean, if you put FEH, we know that F means 1111 and E means 1110. Or we can say F is 15 and E is 14. Now, you will notice that we write 1111 because the 4 LEDs on the left, which is position number 6, 5, 4, and these LEDs must be off. So to turn it off, we should put 1111. And then the LED 3210 must be also off except the first LED, which is in position 0. So we have to do it like 1110. Of course, if you will do it in the normal way, what we usually do is 0000, This means that the first or the LEDs from the left will be off, 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 and then on. But since this is active low, what will happen is the off will be 1. That's why this becomes 1111, which really means on. But in the case of active low LEDs, this will become off, 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 and then off, 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 and then on. Therefore, instead of writing 1 to turn it on, we will be putting 0. Now, take note that in binary, we have to convert it to decimal numbers. So it will be, or in hexa, so we have to put 8421 and another 8421. So if you want to get 1111, you will have to add 8 plus 4 plus 2 plus 1, and the answer to that will be 15. And we know that 15 is letter F. Now, for the 1110, it's actually 8 plus 4 plus 2. That will be plus 1, but plus 1, we will not do plus 1 because it's 0 here. So 8 plus 4 plus 2, that will be 14. And the 14 in decimal, if you convert it to hexadecimal, will be letter E. That's why in our program, we have to write FE. This is to turn on only the first LED on the rightmost side of the 8 LEDs. That is position 0. This one. This position of the LED. Now, also there's a rule in assembly that when you write a number and it is hexadecimal number, it should not be starting with a letter. So if your hexadecimal number is hexadecimal number 28, it's okay because the number 2 is a number. But if your hexadecimal starts with letter A, like A9, then you have to put a prefix of 0 before the letter A, or else there will be an error in your program later on when you assemble it. So we will put 0 here in the beginning, and we did this so that we will be turning on the LED on the right side. But we cannot do it directly because in C language, what we put is P1 or P10 is equal to 0x or is equal to 1 if it is active high. P10 equals 0 if it is active low. Now, if you want to do it by using P1 in C language, it's 0x. Let's say it's active low, so 0x FE. So if it is binary, it will be like 1111 1110. So it's active low, so it will be off, 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 and then on. This is how we do it. Directly you can immediately put FE to P1. But in the case of assembly, whatever you want to put to P1, like here, you cannot say move P1 and then you will move directly the value of FE like this. You cannot do that. Instead, what will happen is that the FE or hexadecimal FE must be placed to the accumulator A, and from A, it will be passed or moved to P1. So what's actually happening here is that A will be equal to FE, and then P1 will be equal to A, which is also equal to FE, or which is also equal to 1111 11110. Okay, so that's the procedure that we will be doing. Now, after that, we have to, of course, put a delay. So, in assembly language, we cannot write for x equals 0, x less than 10,000, x plus plus. We cannot do that. Or we cannot write ms delay like this. No. Instead, we have to use a command which is call, and then the name of the delay that you want to call. Let's say I will call the name delay. And then this delay must be declared here at the bottom or the lower part. We call this label in assembly. And we will write delay and then followed by what you want to do in the delay. Now, for the delay, we usually move a number to a register. For example, move to the register 0. Let's put the number 100. So you can do that. And then from here, we will be decreasing this number or decrementing this number. We will write DJ and Z, and then R0, and then comma, and then delay. So what will happen here is that the R0 will be equal to R0 minus 1, and while the R0 is not yet 0, you will go back to delay label or to the delay subroutine. So you will always go there. But if the R0 becomes 0 after subtracting 1 from it every time, then you will return to the calling part here. And after that, when you finish the program, there should be an end here. Now, we don't really write 100 here as a decimal number. We can also write it as hexa. And if you convert 100 decimal into hexa, it will be 64H. Now, in this case, this is 6. We don't need to put extra 0 in the beginning. So this is in a hexadecimal number 64. Although you can also write hexadecimal number 100 or decimal number 100, but don't put any letter anymore. So either you use 100 or you use 64. And then this part, DJNZR0, will actually subtract 1 from it. So from 64, it will be 63, 62, 61, and so on until it reaches 0. Now, if it is in decimal, it will be 100, and then 99, 98, 97, and there you go. That's what will happen. That's why we will have a delay like that. Now, we can also put another number here, register. Let's say we put delay 1, colon, and then we will move another to another register R1, for example, a number like 10. Okay, so that we will multiply 100 by 10. It will be like making a delay of 1,000 counts, or it will be from 1,000 and then 99, 98. It will be just counting from 1,000 to 0, because 100 multiplied by 10 will be 1,000. But if you want to write it in hexa, then it will be 0A hexa. So what will happen here is that the register 0 will be 64H, register 1 will be 0AH, and then we will deduct or decrement the value of R1. So we will put DJ and Z R1, and then we will tell where it will go back. So let's say it will go back to again. And on the left side here, we can write a label again. In other words, while the R1 is not yet 0, it will always be going back to again. So in other words, this will count from 10 to 0, or from A and then 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. In other words, it will count 10 times, and after reaching 10 times of counting or delaying, then the 64 will be decremented again. It will be 64, and then 63, it will count by 10, it will be 62, it will count by 10, it will be 61, and so on. So it will actually, the 64H is like 100 in decimal, and 0A is like 10 in decimal. So the delay that we will be doing is actually 100 multiplied by 10. That's actually 1000, 1000 down to 0. That's what will happen. Or we can say that it's from 64H down to 0H, or multiply 64H multiply by 0AH. That will be approximately 1000 in decimal also. So that's what we are doing here. Now, it's better if we will demonstrate what will happen here, but let's continue this part. So after you have made the first LED to turn on, then we will turn it off. And to turn it off, I just copied the first part of the program, first three here, or the second line, third and fourth, and I will make this E to become FF. Now you may ask why I made it FF. It's because the leftmost four LEDs will all be off, and the rightmost four LEDs will also be off. And that will be off because this is active load. In the beginning, we made it off, 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 on. So here, we have to make it all off except the rightmost side, which is on before. Yeah, in the beginning, only the first LED is on or off, and then in the second part, that will be on. So here, it's actually on, and here, this will be off. That's what will happen. Now, it's better if we see this happening when we run the program. So look at this closely, and let's try to click the ASSM. So if you click this and there's no message, then our program is okay, and then let's run it. Now, when you run it, you will notice that the numbers here in the data memory are starting to count, and the LED here is not blinking. It's because you have to change the frequency over here to make it run faster. Like, for example, if you put 100, it will be counting faster, but to get that faster frequency, we will use 10,000 cycles per second, so that when we run the program, the LED here will be turning on and off faster than the first part. Now, let's see why this is not turning on and off. So we have move A, hashtag 0FEH, move P1A, we call the delay, and then move A0FFH, move P1A, we call the delay. I forgot to put the jump so that it will go back to the main label. So I put a short jump here, or jump. So it will just go back to the main function, or to the main label from here. So let's try it again, run. Okay, so now let's pause and let's check on the delay. So the delay is move R0, 64H, move R1, 08H, DJNZ R1, we have the again, and then DJNZ R0, we have delay, but this should be delay 1, not delay only, but delay 1. And so this is I think this will be now okay. Let's try to click assemble. It's okay, run. Yes. So as you can see, our LED now here is blinking. Now you will also notice that the 7-segment indicator here is blinking because as given here, the P1.0 is not only using LED 0, but it's also using segment A of the 7-segment indicator. So that's how it is by using the assembly language, and we can copy this code so that it will be better if you can see it from here. So this is actually our program based on our assembly language problem solution. Now you will see here that the memory started from 0000 because we declared it as the origin over here. And so you will also see how much was jumped from 0. It became 2. It jumped to 2 places, or 0, 1, and then 2, and then here 2 places again, 2 places, 2, 2, 2. So usually the memory that is used consists of two storage areas. And the delay was in 0E, and the delay 1 is in 10, again is in 12, and then this is 14 and 16. But of course, if you want, you can also copy from this part. Okay, and you can put it over here. So this is our program. This is our assembly program with some simulation. At least you will see what's happening. So this is problem 1. Again, let's say this is the solution to our problem of blinking the LED. So the main command responsible for this is this part, because this means 1111 1110. So the P1.0 LED will be on, and then here this is the 1111 1111. So what happened here is that port P1.0 LED will be off, and then this delay will give some delay. It will give some delay, and that delay will be starting from here. Okay, and 64H means 100 in decimal. And then here there's another number that we put on register 0A. 0AH is actually 10 in decimal. So what happened here was, like, we multiply 100 by 10, we will get a delay of around 1000. So, and of course, it depends on the frequency that you will use here. So take note, I use 10,000. So when we run it, again, this is the result. So I hope you learned something about the introduction to assembly language programming using 8051 microcontroller. And this problem is very easy. It's only blinking one LED among the 8 LEDs available in our simulator. Of course, if you want to make the other LEDs blink, then you just need to change the numbers over here. And just remember that when you put 1, that means off, and when you put 0, that means on. So try making the LED on position 1, position 2, up to position 7 to blink one by one, and practice on this example. Thank you so much, and I hope you will subscribe and share this YouTube channel, YouTube video, and like it, and click the notification bell. But of course, we need your support so that we can help other students or beginners in programming, especially those who wants to make a project that make use of the microcontroller. Thank you so much.